we are flipping the order today. Now, typically I show this as my last slide, which is where the slides are available. But you saw me downloading the slides live from my GitHub repo. So essentially, the slides that I'm using in the session today are available at this GitHub repo. So feel free to use the slides, share them. This is a continually evolving slide deck. So as I add more content to it, I update the slide deck, and I push them on the GitHub repo again. All right. Now, how many of you are using some sort of container in your day job? Some sort of Docker? Okay. All right. I see almost 60, 70% of the hands. Now, this is not a Docker 101 talk. I don't expect to give basic concepts of Docker in this. I presume you understand what a Docker image is, what a Docker container is, and things like that. And you have a little bit of knowledge around Java as well. If you don't know Java programming, that's okay, because I'm not going to get into programming here. But I will be explaining the concepts of Docker and Kubernetes. How do you package your applications? I'll be using examples of Java, but by no means this is restricted to Java as such. So who am I? I'm a Docker captain. There are about 70 of us around the world, which are recognized by the company Docker Inc. We talk about Docker around the world. I'm also a Java champion. And I also speak about these topics around the world at different conferences. Now, if we look at a very high level, not. Anyway, so if you look at Docker, how do things operate, behave, work in Docker? There are three key components. One is sort of the CLI, what you see on the left-hand side, or the Docker client. Then in the middle is a Docker host. There is a Docker client which tells a Docker host that I need to run a container, I need to build an image, or I need to do something with a container or an image. Now, client is pretty dumb. Client doesn't have any state. Client tells the host to do something, and host is the one that maintains the state. Now, if you want to run an image, if you want to run a container, if you want to build an image, all of that is done on the host. But if an image does not exist, then it can download the image from a public registry, which is typically Docker Hub, as you can see on the far right here. So the point being, these are the three key components: client, host, and Docker registry that you're looking for in a typical Docker workflow. And in this case, you can see typically a client is single point of contact here, but Docker host is a single point of failure, because if your images and your containers are everything only on that single host, and if that host goes down, everything breaks apart. So typically you will have a variety of hosts, multiple number of hosts on which you will schedule your containers. And that's exactly where your container orchestration platforms come in. So essentially, if you think about it, Docker, typically people confuse Docker means only the container format. Docker also has a container orchestration platform, which is called a Swarm. So today what we'll talk about is how can you package your Java applications, how can you run, deploy, scale your Java applications so that they work not only in Docker Swarm, but also in Kubernetes, which is the alternative orchestration platform by CNCF. So from the developer perspective, what we'll take a look at it today, what are the core concepts of Docker Swarm? Can you spin up a Swarm cluster? How can you scale the cluster? How can you spin up a multi-container? First of all, what is a multi-container application? How can you do service discovery? How can you do persistent volumes? How can you run stateful containers? So those are some of the key concepts that we're going to look from the developer perspective. On the right side, what you see is some of the ops perspective. How do I set up a cluster? How do I do a rolling deployment? How do I do monitoring? How can I set up constraints where I can tell where exactly to run your container, like which particular host to run a container on? Because when you set up a cluster, it might have been set up accordingly. So, and then those are the key concepts that we're going to look from the dev and the ops perspective, again, from a Java developer's perspective. Let's take a look at it. Now, at a very high level, when you have a single Docker host, you can initialize Docker Swarm over there. That means you can say, by the way, start up a Docker Swarm cluster. To begin with, it's a single node cluster. It's an optional command, but you need to say Docker Swarm init. And once you say Docker Swarm init, you're saying, okay, initialize the swarm. Now, depending upon where you are running, if your host has multiple IP addresses, then you got to say -- listen address. And what that means is, okay, I am going to listen on this particular network interface. And whatever the IP address is, there's a default port for it. So that's where you can very easily start a single node Docker cluster. When you start, by default, the single node cluster is running in a manager mode. On a manager, you can run containers as well. So a single node cluster works very well for development purpose. But then pretty soon you want to add a worker. You want to create a multi-node cluster. And what that means is you have another machine or another virtual machine or another laptop that you want to join as part of this cluster. So the one in the middle, yellow, is a manager. The one in the orange is a worker. So from the manager, you'll get a worker token or a manager token, and you will pass that token to the machine that is joining the cluster. And based upon that, that machine will join the cluster either as a manager or as a worker. Similarly, you can have other machines join the cluster. You can have multi-node clusters set up very easily, depending upon the commands that you execute over there. You can also have multi-master cluster, because if you have a single master, that essentially becomes a single point of failure. What that means is your command goes to a master that, okay, run a container or build an image, and then the master figures out where the command needs to be executed. But if that master goes down, then the command bounces back essentially. So you want to make sure that you have a multi-master cluster so that in case one master goes down, the other master can come up. We'll talk about how does that really work. So give it a few minutes. Now, if a command goes to a secondary, then that is automatically proxied to the primary. They already run a consensus protocol among themselves. So the primary is the one that is responsible for running the commands, and it delegates the commands to all the worker nodes that are sitting in the cluster essentially. So multi-master, multi-worker cluster kind of gives you that truly distributed architecture, and you don't have a single point of failure also. Now, within the manager itself, the way Docker Swarm cluster is set up, they highly encourage you, they strongly recommend you actually to have either not one, 3 or 5 node cluster for the managers. And that is because if you run even number of clusters and if the network is split, then you don't know which one is the leader at a given point of time. Within the managers itself, it runs a Raft consensus group, which is strongly consistent. And by having an odd number of managers, it also ensures if there's a network partition, then a leader can emerge and then make the calls accordingly. Within the swarm, they all talk to each other using gossip network. And what you're seeing here is, for example, in this case, I have 3 containers running as part of a service that are spread across multiple hosts. Similarly, 2 containers, the green containers running across 2 swarm workers. I can also configure here my manager to be running only in the pure administrative mode, where no containers are running on the manager and the managers are only for administration. By default, you can run the containers on the manager as well, but they can be configured either way. Okay. Now I have a multi-master cluster, multi-manager, multi-node cluster, and I want to run a simple service. I want to run a simple wildfly container over there. Well, what will I do? What I'll say is Docker service create, that's my command. So remember, go back to my flow earlier that I explained. Docker is my CLI. I'm giving it a command service, and I'm giving it a sub-command called as create. Create the service. I want 3 instances of the service, give service a name, and then I give it the image name. So what's going to happen? You're from the CLI, you point to the master that create this service. It's going to create the service. It says, oh, by the way, I don't have the JBoss wildfly image. I have figured out using my internal algorithms that these are the 3 nodes where the container is going to run. And by running the container, that means I need to download that image on these 3 hosts. So it's going to go by default talk to Docker Hub, which is a Docker public registry. It will look for the image, download the image on those 3 nodes, and run the container on those 3 nodes. So that's sort of the way typically it will work in terms of how the service would be created. Now the beauty of this is Docker maintains the state. It says 3 replicas of the service, it'll make sure 3 replicas of the service are running. So if an instance of a service goes down, it'll automatically bring up an instance of a service. So you don't need to monitor as such if a service has gone down or not. You said 3, it'll ensure 3. Now, at any point of time, your node can fail, because ultimately it's a virtual machine or a hardware that are meant to fail. But if a node fails, what happens? Well, the Docker engine or the Docker master recognizes, oh, node has gone down. That means my desired state is not equivalent to the actual state. Desired is 3, the actual is 2. So it just simply reconciles. It says, all right, you know what? I'm going to spin up a new container on a different host. It just assumes that the host has gone down, either using heartbeat or in a constant ping. And once it figures out the node has gone down, it'll automatically fire up a host or a container on a different host for you. Now let's say the host is good, but for some reason your container has gone down. Well, if the container has gone down, again the same thing. Because you've said Docker service create replicas 3, it needs to maintain 3 replicas, it needs to maintain the state. It again says the desired is not equivalent to actual, and then it will fire up the container on a different host. Now, how does it impact? What is the scheduling algorithm? We'll talk about that a little bit later. But think of this as an algorithm that is available to manager, and there are certain ways by which you can influence on where to fire up my container at. I want to scale my service. Okay, I created a 3 replica service and 3 instances of Wildfly are running, and now I want to say scale it to 6. Once again, my CLI, my command, my subcommand, and my service name and the number of replicas. I'm saying Docker scale service web, which is service name equal to the number of replicas, and the Docker manager will accordingly schedule those 6 containers or other 3 additional containers on the cluster. Now, so far what we have talked about is the concept of a replicated service, where I can say, okay, so I run so many replicas of a particular service. I could also have a global service. So for example, Prometheus is a container or is a service or a process that can gather your monitoring statistics for a particular host or different containers on that host. So now I want to run a service. I can say Docker service create. I'm running a global service as opposed to a replicated service, which is the default. I'm running a global service, giving it a name and my image name. Now, by default, on each node of the cluster, I'll have a single instance of the Prometheus service or the container running. If a new node comes in, it'll automatically fire up that particular container on that host as well. If a host goes down, it doesn't matter. But the point being, at a given point of time, there will be a single container running on each of the hosts. And then how do you coordinate those different containers? You know, what information is being spit out from that container? Where is it stored? That is completely up to you, though. So that's sort of my core concepts of, you know, if I wanted to run up a Docker Swarm cluster easily. Let's take a look at Kubernetes. Now, typically this shows up with a nice animation, but this is what you get for using a Windows machine. Now, the way, you know, we understood the basic concepts of Docker. Yes, there is a Docker host, there's a Docker image, there's a Docker container that runs over there. On Kubernetes, you start with that as the baseline, that yes, there is a Docker host. And now Kubernetes says, Kubernetes is, first of all, is an open source orchestration framework, originally built by Google based upon their experience from running containers over a number of years. And then this framework was really donated to CNCF, or the Cloud Native Computing Foundation. And that's where it's being built, you know, collaborated by multiple parties around the world. Now, there is a Docker host, as you see on the image on the top right, which is a blue box. Kubernetes introduces a new concept of called as pod. It's a new abstraction layer on top of the container. The hardest part for me to figure out was why there's a need for a pod. If I'm running a MVC application, does that mean my model, my view, my controller? If I'm running a 3-tier application, does that mean all 3 containers are going to run in a pod? If you think about it, pod, in that sense, is just an additional abstraction. And idea is, if you are running a multi-container application where you have a database container, a web container, a web server, and so on, different components, all of those three containers would be running a single instance of a container in a pod. Then what you would do is you would scale a pod, and then accordingly the container would scale. Now, in certain cases, you may want to run a primary container and a sidecar container with it. So, for example, you may want to run a Wildfly container and a logging container right next to it. And why you would do that is so that it can grab some logging information out of it, or do some formatting, or do some forwarding out of it. Then you may run those 2 containers together in a pod. So that's sort of the core idea here. So typically, the relationship between the pod and the container is 1-to-1. All right, so now I got a pod. In the pod, I'm running containers. Now, the way I scale the service in Kubernetes is using replica set. So I would say, okay, I want to run multiple instances of that pod. So I'm going to wrap them in a replica set. And now I can say, run how many replicas of a replica set. Then, well, each pod is given a unique IP address, but the IP address is ephemeral. What that means is, let's say today the pod is running on a certain host. Again, it's a multi-host cluster. If the pod is running on a particular host, and if the pod dies for some reason on a particular host, it may come up on a different host. But what that means in that case is, essentially, it will be given a different IP address. Now, think of an example. You have a Java application and a database application. Think of a typical Wildfly or Spring Boot application talking to a MySQL or some other database. If these were to talk to each other, typically they would be having a JDBC URL or some sort of a HTTP URL or a host and a port combination by which they need to talk. But if I am relying upon an IP address of a pod, I cannot do that because it's ephemeral. And if the pod dies and comes up on a different host, that doesn't matter to me because my application is going to break apart. So that's where the concept of a Kubernetes service comes in. In Kubernetes service, essentially what they say is, you can have a service, in this case a DB service. I have a Couchbase pod running here, 2 pods running, and in each pod I have a Couchbase container running here. I can expose the ports that are coming out of the container, and then I can have a logical name to the service. The logical name in this case is DB. Now, so what service gives you is a logical name to the service, and the way which pods become part of which service is identified using labels. It's a very loosely coupled concept, but essentially, this particular pod will have certain labels. This particular pod will have a similar set of labels, and this service is looking out for those labels. It says basically, anytime a pod comes up and it has labels, make it a part of me. And then from the application perspective, you will be accessing the database using that logical name. Now, in terms of how the cluster is structured, just like there is a multi-master in Docker Swarm, there is a multi-master in Kubernetes as well. There are other core components here. If you look at the master here itself, there is an API server. Now, if you look at the Docker CLI, that's a dumb client, but when it talks to the Docker host, it's basically using a REST API behind the scenes. And essentially that REST API goes to the Docker host, which interprets the REST command, does the execution, and responds back with a REST response. Similarly, there's an API server here. There is a kubectl, which is a Kubernetes CLI, which talks to the API server, does all the processing and returns the response back. There is a scheduler within the master itself, which figures out where the pod needs to be scheduled, which host it needs to go to. Then there's a controller manager, things like replica set, which says, okay, spin up a new pod for me. So the controller manager manages those controllers essentially. And etcd is a distributed watchable registry where the labels are stored essentially. Because you're storing your labels over there, it's distributed across your network, and the controller manager is keeping a watch on that registry. Oh, a new pod has come up, and I'm subscribed to those pods. Let me pull them up make them as part of my service. And then finally, on the worker side of it, of course, you have a Docker host. This is where your pods are running. And then you have a kubelet, which is sort of a node agent on the worker, which is responsible for running the pods and ensuring their life and everything else. And then there is proxy, which is, let's take a look at that next, actually. So at a very high level, if I were to look at the Kubernetes cluster, it's very similar to what we looked at Docker, essentially. I have a kubectl API. The kubectl API, to the kubectl API, I give it a configuration file. That configuration file has a description of the resources that need to be generated. That command goes to the master, which is basically an API server. That API server then talks to the two kubelets, saying, okay, I need to schedule a pod, and a kubelet is responsible for running the pod on that particular host. And then on the right side, when I say internet and load balancer, that's essentially my client application. My client application is coming from internet, talks to the load balancer, which then talks to the proxy and figures out which particular pod is going to serve that request. So that's sort of the overall sort of a flow chart or the logical diagram of how the Kubernetes cluster is laid out. Now, we talked about the concept of service discovery a little bit, why it is important to have service discovery. And that is primarily because you cannot rely upon the IP address of the pod or the container, because if they do get rescheduled, then what that means is they'll be given a different IP address. So you need a logical name. Now, in order to run an application where I have a Java application and a database, and they're talking to each other, those are essentially two containers. So what I'm talking about is a multi-container application where multiple containers are running together as a single application. So the way it's done in Docker is using Docker compose files. And honestly, what I'm doing here is I have a docker compose.yaml, which is the default file name. In that default file name, I specify exactly what containers need to be run. I could have a docker compose override.yaml, in which I start giving more details about what services need to override. And I'll show you the use case where it's very relevant. If need be, I can run multiple files, and that particular use case is very relevant if you want to run, if you want to minimize the production or the impedance mismatch between dev and the staging and the production and so on. Okay. Now, this multi-container application is deployed as Docker stack, and it is very great for reducing your impedance mismatch. Let's take a look at it. This is how I built my application. Now, in this case, this is a Docker compose file. In this, I have, I'm defining version 3. I'm saying I'm defining services. I have a DB service and a web service. In the DB service, I'm giving the image name. So this is sort of my image name. This is my another image name. This is an application that is a Java EE application, which is baked into Wildfly itself. And all I'm saying is this image uses an environment variable by the name Couchbase _ URI. It reads that environment variable. And in my case, I'm saying the value of that environment variable is pointing to this DB service. So essentially, if I take this Docker compose file and I give it to a Docker cluster, it'll download those images for me. It'll run those containers for me. And those containers will be pre-configured to talk to each other. So literally with a single command, I've been able to fire up a multi-container application very easily and doing service discovery as well. That's sort of the design pattern that Docker is recommending to use when you're building your multi-container application. Now, yes, I'm using Java and Couchbase here, but does not mean you cannot use any other stack. You can use, this could be Ruby, this could be Node.js, that could be any database that you care about. So the idea is to understand the design pattern first of all. So essentially what I do is I run a stack. In a stack, there are multiple services, and now I can scale each of the service independently, and the service will run that many tasks. And essentially each task corresponds to a container. That's sort of your very high level encapsulation you want to understand. Now, one of the cool things is, let's say you have running a 6-node cluster here. Now, your load balancer, your front-end load balancer, whether it's Apache, Nginx, F5, pick your load balancer, those are host aware. What that means is the load balancer knows there are 5 hosts running in the cluster, but it is not container aware. So how does that work? Now, Docker has this thing called as routing mesh. So in your load balancer, you still configure that I got these 5 workers that I want to be load balanced. The request comes in to your load balancer, and it can go to any of those 5 nodes. Now, let's say it goes to this node where the container is not running. Now, in this case, what will happen is using IP virtual tables, it will automatically redirect the request to the host where the container is running. Now, you may think it's a costly operation, but it's a very minimal cost operation. You don't even notice it as a matter of fact. So from your perspective, you have the flexibility because the containers can die on a particular host, come up on a different host. So you only need to configure essentially, hey, this is my load balancer, and these are my 5 hosts that needs to be configured as part of the load balancer, and then let the cluster dynamically scale in and out. So today you have like literally running 1 container on this host. Tomorrow, if you say scale the service to 6, then you will have more containers running on all the hosts. Well, there is an internal, because essentially, yes, I agree, because load balancer, you will set up an algorithm essentially over there on what the algorithm needs to be. And that's something you need to play with, because within the service, how you accessing it, there are algorithms for the service as well. No, they won't. They won't. Now, how does service discovery work in Kubernetes? Very similar concept, as a matter of fact. There is a service concept in Kubernetes as well. It basically takes a set of pods and expose a single IP and a port to them. It creates environment variables in other pods that you can then start accessing. And it does, again, using DNS resolution. So if you go back to our Docker Compose file, I'm taking a web application talking to the DB service. The DB is a variable that is available to you, and that is done late resolution to the IP address exactly at the runtime. Same concept works here as well. So let's take a look at it. How would my configuration files look different in this case? It looks prettier with an animation, but let's try to walk through this. Now, this is a big configuration file from the Kubernetes perspective. Let me walk you through this, how this looks like. Well, this configuration file is divided into 3 parts. And these 3 dashes are sort of the separation of the 3 parts, first of all. Now, the very first part basically says this is a service. The second part says it's a replica set. And the third part is also a replica set. Now, typically, if I'm running my Wildfly application server, I may not run it as a single pod. Because if I'm running as a single pod and if the pod goes down, I have no way to control it. I can set up the replication policy on the pod, but typically I would wrap that pod into a replica set as well. So in this case, for example, I'm running my same image wrapped in a pod, wrapped in a replica set here. And in here, I'm saying run a single replica of that pod. So I'm basically running a single Wildfly container, a single Wildfly pod essentially here. Now here, I'm running a Couchbase pod. If I look at this, this is my image name here, Arun Gupta Couchbase :travel. I am giving it certain labels that, okay, when I run this pod, give it the label app Couchbase RS pod. And then on the far left here, when I'm running my service, I'm saying, okay, when the service comes up, it is looking for any pod that has these labels, app, Couchbase, RS pod. So the label is nothing but a key value pair. You assign that key value pair to your pod, and service has to watch for it. That's what it is basically. It's a completely arbitrary value as you want it to be. But the key part being service is looking for those labels and the pod has those labels, and that's how the pod becomes part of that service. Now, if we go back to the original example of Docker Compose, I had Couchbase URI here. That's the environment variable that my application is looking for, and that's the value that we are pointing to, that the value of that environment variable is Couchbase service. So just like Docker Compose, there is a DNS resolution that happens. I'm just looking at the Couchbase service as the value, and then I run with that. So essentially, if you look at the deployment diagram once again, I have a Wildfly application that will talk to a Couchbase service, which will then delegate it to the Couchbase pod. Now today I may have a single container running or a single pod running. Tomorrow I can scale the container very easily, and then it'll still be able to load balance across that cluster. At a very, if you up-level the discussion, yes, you could have a front-end service, and you can have a back-end service. All the pods in the front-end service will talk to the Couchbase service, which will then talk to the back-end service. Now you need to think about it, in terms of Couchbase, how the clustering works. In terms of your database, how does the clustering work? Is the read going through all the nodes, or is the write going through all the nodes? Or is there a specific node that you need to go through? So you have to really do that matching of how does load balancing work in the service side of it and in your database cluster side of it. So that matching is sort of critical. Load balancers are not sticky sessions. So that's where we will talk about the persistent volumes on how the stateful containers need to run. Well, that's actually the next topic right here itself. So if in Docker, if you're running your persistent containers, what that means is, if you look at your typical containers, those are stateless. What that means is, you are running a container like a web application. If the container dies, it can come up on a different application. There is no state. All the state is stored into the database. If the container comes up on a different host, it can recover that from the database. Now, at certain times, you may want to run your database in a container. So in that case, there are 4 different models in the Docker side of it. There is implicit per container storage. If you fire up a container, take the example of Couchbase, for example, in this case. If I fire up my Couchbase container, there is a default directory where it writes to. That directory exists within warlib Docker volumes on the host. Or I can explicitly create a volume using Docker volume create command and give it a specific volume name. Or I can do volume mapping, in which case I'll say, oh, by the way, when I'm firing up my database, I know the database writes to OPT war Couchbase. Map that directory in the container to a directory on my host. And then last but not the least, which is typically what people use for production usage, is do the storage on a distributed file system. So let's see what are the pros and the cons for each of these. Well, of course, in this one is the implicit per container is the easiest to start with. The location is warlib Docker volumes. In this case, again, the location is warlib Docker volumes. This is mounted within the container, but is mapped to a local directory. This is typically using Ceph, Gluster, FS, NFS, one of those distributed file systems. In both of these cases, if the container crashes, the directory is unavailable to you. Because the container has crashed, you have no way to access the directory. Actually, in this case, this needs to be changed because it is still accessible by using the volume name, because I'm giving it explicit volume name. In this case, there is no volume name, so this is not accessible. These are slightly older slides. In this case, because the directory is mapped onto the host, so even if the container dies, I can fire up a new container, use the same volume mapping, and then it'll be able to read the data back for you. And in this case, of course, this is completely host independent as well, because my volume is living in a completely remote host, say EBS or somewhere else. Container dies, container comes up again, and it maps to the same network volume, and we're golden. In terms of host crash and AIS, both of these are not available because the directory is on the host. In this case, again, host is crashed, it's not available. But in this case, because the volume is mapped on a remote host, the directory is very much accessible to you. And then similarly, there is a row for whether the volumes are shared or not shared. Now, typically, when people are going into production, they're typically using the Docker Volume plugin. The Docker Volume plugin kind of follows the architecture of batteries included but replaceable. So if you look at the Docker architecture, in terms of Docker architecture, it allows you a default plugin which allows you to store the volume on the host, which is the implicit sandbox essentially. Now, in this case, what it allows you, there are plugins that are available which allows you to persist that data on network volumes. Now, this could be Amazon EBS, Azure Storage, GCE Persistent Disk, NFS, any distributed file system that you can care about. So how does this architecture work like? Now, so by default, I have a Docker client and a Docker host that knows how to write to your local file system of the Docker host. That is the only architecture that is available to you by default. But that architecture, the way it's built is writing to the local file system is using a plugin architecture, using a plugin. So essentially, you could have a plugin daemon fit right in there and a plugin client which will talk to the plugin daemon. And this plugin daemon could enable a variety of storage backends for you in the, for the container to run to. So for example, the one that I played with is Portworx. Now Portworx, my same Docker client would write to a Docker host, but once I have configured the Portworx plugin, then using Portworx plugin, I can easily write to Amazon EBS. And I don't need to worry about volume mapping. And the advantage is, if Portworx also run an etcd container, where it says, okay, which host, which container, and which volumes are mapped to each other. And if a container goes down, if the container comes up on a different host, it automatically mounts the volume to that host. So that if the container goes down, your container can come up, your state of the container is restored on that particular host automatically. And of course, there is a Portworx client, which essentially allows you to manage the state of your Portworx daemon. In Kubernetes, again, there is a similar concept. There are directories that are accessible to the containers in a pod. They define this concept of a volume or Kubernetes volume. Kubernetes volume outlives any containers in a pod because you have a pod. In a pod, you have multiple containers. A pod can die, the pod can come back up again. But if the pod dies, then the volume is inaccessible. Well, that's where they have this concept of Kubernetes persistent volume. So how does this Kubernetes persistent volume work? Well, Kubernetes persistent volume, it's a three-step process. Essentially, somebody provisions a network storage, which says, here is my EBS volume, or my GCE persistent disk, or my Azure storage. Somebody has provisioned like 10 gigabytes of those. Then a system administrator, again, would request a storage, would say, okay, I'm going to make a claim of that storage. Give me about 2 gigabytes of that I need to use for my database. And then you can use that claim into your configuration file itself when you are actually running up your database container. So it's a three-step process. The first two are typically done by a sysadmin, and you may end up doing that during your development phases. There's a blog URL at the bottom which says exactly more details about how do you configure a Kubernetes persistent volume. So what that gives me the ability is, well, I have one master, two workers running over here. I have a Couchbase pod running over here with a service over here. And then the Couchbase pod is writing to a storage on a worker. Using persistent volumes, Kubernetes persistent volume, I can say, oh, you know what? Write it to Amazon Web Services. By default, you were writing to the local host, but that doesn't help me scale. So now write it to a EBS volume. So if my container dies or a pod dies and comes upon a different worker, well, that's actually the Portworx architecture. So I have a Portworx agent running on each of the hosts, which knows the mapping of the container and the actual EBS volume. So if my container dies on one worker and comes upon a different worker, it will automatically do the volume mapping from this host to this host automatically. And that's the magic that, so to say, Portworx provide in the backend. Now, in terms of development, how do you get started? Well, in Docker, there are two editions. There is a Docker Community Edition and a Docker Enterprise Edition. Docker Enterprise Edition is for the production commercial side of it. But from the from the development perspective, there is a Community Edition. If you look at the Community Edition, again, there are two different releases. There is an edge release, and then there's a stable release. Stable release is done once every 3 months, and then the edge release is done every month. So if you want to live on the bleeding edge of Docker, just go to docker.com/getdocker and download the edge release. You'll always have the latest releases from Docker. I run Docker for Mac. It's a native DMG application that installs on my MacBook, and then I run Docker that way. You can do that on a Windows box. If you're using Windows 10 as your corporate IT machine, then you can use Docker for Windows, but otherwise there are older tools that you can use on older machines as well. This is the native way to build your applications on desktop, and then they have Docker for AWS and Azure, by which you can build those applications very easily in the cloud as well. In terms of Kubernetes, you could run a single node Kubernetes cluster very easily using Minikube. So Google for Minikube, and it'll give you a link on how you can download that Minikube DMG, and then you can, or a script basically. Then you can run a simple VM. Now, depending upon what operating system it is, it spins up a native VM for you. Or if you want to do a multi-node cluster, then there are a few options essentially. So you can use kops or kube AWS, or there are other CloudFormation templates that you can use to spin up Kubernetes on AWS, for example. Let's talk a little bit about rolling deployments. Now, what is the concept of rolling deployment? Well, the concept is, again, looks better with the animation, but I have a particular version of an application running, say a version 1. And now, what I want to do is, in a rolling fashion, or say 2 at a time, I want to update version 1 to version 2. Okay? Now, the way I will do that is, I will say Docker service, again, CLI command, service update. Which service am I updating? Then I'm saying, okay, give it a new image, and I'm giving it the new image name and the tag. I'm saying update parallelism. That means update 2 instances of the service at a given point of time. And once you have updated 2 containers, wait for 10 seconds for the containers to settle down, or the cluster to settle down, and then do the next update. So essentially, it'll pick up in random order. It'll update 2 containers, then wait for 10 seconds, then update 2 containers, wait for 10 seconds, and update the last 2 containers. So that's sort of the order in which it'll update the containers. So that gives you the ability to do rolling deployments. In terms of Kubernetes, there is a similar concept as well. Well, Kubernetes, of course, we have this concept of a replication controller or a replica set, which is where what I want to do is I want to update all the replicas of my application. Let's say I'm running version 1 of a Wildfly application, and I want to change that to Wildfly version 2. So the way it works out is, I know it looks messy because it's not animated yet, at least in this case. But essentially what happens is I have version 1 running over here. It'll fire up a new replica set with version 2. And once it is fired up, then it'll slowly start terminating version 1. All those version 1 would be gone. And then it'll rename this web app replica set, giving it a random name to begin with. And then it'll rename it to the web app RC, or whatever the original name was. So there is a time where more instances are running, but there is no instance where there are less instances are running. So that way, you can do sort of a A/B testing as well in case you want to, by running a couple of replica sets and see which replica set is behaving and meeting your needs and requirements. So what are my options if I want to monitor my applications? In terms of monitoring my applications, there are a few options that are available to me. Is it looking good now? Okay, let's try it again. It works this time. Okay, can you hear me now? All right. In terms of monitoring the Docker container, there are different options. In the CLI itself, I have this option, API called as Docker Container Stats API, which gives me sort of, every second a snapshot of what the container looks like. And as part of the API, it gives me, for example, CPU usage, memory usage, disk I/O, and it gives you the % utilization and the actual utilization. So this API is pretty handy. It comes as part of Docker. There is no fancy tool required for that. Now, there is also a Docker remote API. And if you go to my blog, blog.arungupta.me, and on that blog, I recently talked about how can this remote API be used to monitor your Docker containers. The remote API, again, is a very raw API, but it gives you a lot more details about your containers. So if you want more fancier details and use that REST API to build your custom dashboards, that can be done. In addition, there is a Docker System Events API, and what that gives you is you are firing up like let's say you're running a multi-node cluster. Now you are firing up a container is getting killed, or a node is going down. Those are all system events. So you want to start monitoring those events. So Docker System Events gives you exposure to that part of the Docker ecosystem. Now, starting with Docker 1.13, which was released a few months ago now, there is an inbuilt Prometheus endpoint. And that actually is giving you a lot more logging information already. And the advantage of using a Prometheus endpoint is you can front end it with, or first of all, back end it with Prometheus and a Grafana and a Kibana dashboards. Things like those can be very easily done. And then, of course, there is Google's C-Advisor, which C stands for Container Advisor. It gives you a lot more fancier results. The thing with C-Advisor is it only gives you data for 60 seconds. So you have to backend that data in a time series database like InfluxDB. And then that InfluxDB can be front-ended with a Grafana or a Kibana dashboard to give you some more details. This is a snapshot of what does the Prometheus endpoint look like. I essentially have a few containers running over here. You can see how the containers have been behaving. You can see the total usage. Well, one container running, but you can see actually four replicas of a container running. So you can see how the total usage looks like. Then you can see usage per core. Then you can see, I can't even read this, very blurry. Usage breakdown. So it gives you some more detailed information. Now this feature is in an early release, so don't rely too much upon this feature. If you were to monitor Kubernetes, now Kubernetes comes with by default built-in tools. So for example, Heapster is a pod that runs as part of Kubernetes that collects all the information by talking to different kubelets and saying, okay, give me more details about the pods that are running, their memory usage, their CPU utilization, all of that. So it collects all of that, and then by default, there is an InfluxDB and a Grafana backend and a dashboard that is running for you. So it collects all that information, stores it into InfluxDB, and it exposes a Grafana dashboard for you. So that sort of a monitoring dashboard is available to you by default. What? It's just different endpoints, because in this case, if you look at it, it's really Heapster, and is collecting the data using C-Advisor. So Prometheus and C-Advisor are sort of a different ways of monitoring information and collecting logging information. And what I'm showing you here is how I can build some fancier dashboards using Grafana and what kind of information I want to collect. Now, of course, there are commercial solutions as well in terms of what you want to monitor as part of Docker and Kubernetes. So sysdig, data, well, I have played particularly with sysdig and weaveworks, a little bit of New Relic as well, and that gives you a little bit more detailed information. Of course, these are commercial products with a 30-day evaluation version. So that gives you some scope to play around with it on what you want to do with it. The slides, as I mentioned, they're already available on this URL, github.com/javaesamples/docker.java. Docker.io is my primary resource on where I get it for all the Docker documentation, and similarly Kubernetes.io for all the Kubernetes documentation. And I think that is my last slide, and we are out of time as well. All right, I will see you at the conference tomorrow and day after as well. Thank you so much.